To start with parallel plate capacitor. Our topic is parallel plate capacitor. See, we have already studied the isolated conductors carrying charges. We have done spherical bodies carrying charges, but there was a limitation to isolated conductor that they can store charge up to a limited quantity. After that, they attain a saturation point because the air around those conductors starts ionizing, and as a result, the charge on that conductor starts leaking out. So to overcome this, we come up with the parallel plate capacitor. This is a special device that can easily store large amount of charge as compared to isolated conductor. Now let us study the basic principle behind this parallel plate capacitor. So we will be doing principle of parallel plate capacitor. Now let us have a plate, and we give any positive charge to this plate. Now when we give positive charge to a plate, we know it can be given up to a certain extent. After that, it will attain a maximum potential and it will attain a saturation point. So we cannot give more charge than that. So suppose that particular stage has arrived. Now we cannot give further positive charge to this plate. Now let us bring another plate near this one. Now this plate B, due to the property of induction, will attain negative charge on its surface, which is near the plate A. Now due to this negative charge attained, the opposite face of plate B will attain a positive charge. Now when this happens, this negative charge, although is equal to the positive charge attained by plate B on the other side, but this negative charge is nearer to plate A as compared to positive charge on plate B. This negative charge tends to decrease potential of A. So due to this negative charge on plate B, potential on A will decrease. Therefore, we can give more positive charge to plate A. Now, next step, so I will be writing it down. When plate B is placed near A due to negative charge induced on plate B, potential of plate A will decrease. Therefore, we can give more positive charge to plate A. So in this way, more positive charge can be given to plate A. But further, now if we connect this plate B to ground, what will happen? Now when you connect this plate to ground, this positive charge will be neutralized. So negative charge from ground, it will travel to this side of plate B and it will neutralize the positive charge on plate B. Now our system will become like this. Second plate B will not have any positive charge on the other side. Therefore, now plate B contains only negative charge, no positive charge on the other side of this plate. So when there is no positive charge on other side of plate B, this negative charge will further decrease the potential of plate A, because now this negative charge will become more efficient because there is no positive charge on other side to neutralize its effect. Now this negative charge will go on to decrease potential of plate A. So now plate A will be in a condition to accept more positive charge. So we can further give more positive charge to plate A. So in this way, plate A, which originally attained its saturation point, was given more positive charge because when we brought plate B closer to it, and after that when we ground the other side of plate B, we are in a condition to give more charge to plate A. In this way, plate A gains large amount of positive charge due to presence of plate B, which is earth. So we can write it like this: when plate B is connected to earth, its effect of decreasing potential of plate A further increases. In other words, potential of A further decreases and plate A can be given more positive charge. So these two steps forms the principle of a parallel plate capacitor, that how bringing a plate B can make plate A to attain more and more charge. Therefore, the capacity of storing the charge increases by this process. This is the basic principle that is working behind a parallel plate capacitor. Further, we will be studying the capacity of this parallel plate capacitor. We will be deriving its expression. So before starting that, you will have to memorize a concept that we did in last chapters. So I will be writing it for you. In last chapter, electric fields, we studied that how we can calculate electric field for a plate or for two plates, one carrying positive charge, another carrying negative charge. So if you can memorize it, we used Gauss law in finding the electric field in three different regions. In case of two infinite parallel sheets carrying opposite charge densities. So what we did, we found that the electric field due to single sheet was electric field due to single sheet it was equal to E is equal to sigma by 2 epsilon naught, where sigma is surface charge density. This is what we proved by using Gauss theorem. So now in this case, we calculated electric field in first region, second and third. What it was, in region 1, this electric field comes out to be electric field due to first plus electric field due to second plate. Electric field due to first plate was negative and electric field due to second plate was positive. We used all the sign conventions that you have to memorize here. So total electric field in region 1 was 0. Similarly, electric field in region 3 was also 0. This was also 0 because it was electric field due to first plate in third region was positive and electric field due to second plate in third region was negative. So total electric field was 0. And in region 2, this electric field was equal to positive for first plate and positive for second plate, and this comes out to be sigma by epsilon naught. So electric field in region 3 comes out to be sigma by epsilon naught. Now we will be using this expression in calculating the capacitance of a parallel plate capacitor. Next we are going to start with the topic capacity of a parallel plate capacitor. We will be calculating capacitance of a parallel plate capacitor in this topic. So we have two plates having opposite charges, and the separation between the two plates, let it be D. So as we have already done, the electric field inside a parallel plate is equal to sigma by epsilon naught, where sigma is surface charge density of these plates. So they have equal surface charge densities, plus sigma and minus sigma, due to opposite polarities. So this is the electric field that exists between these two plates. So electric field between two plates is equal to sigma by epsilon naught. This expression we have done in the last lecture. Now to calculate the capacitance of this capacitor, we will have to first calculate the potential. Now what is potential? We know electrostatic potential is equal to electric field into D. D is the distance between these two plates. Now as we know, electric field is equal to sigma by epsilon naught. Using this expression, we get potential is equal to sigma D by epsilon naught. Now what is sigma? Sigma is surface charge density, and this is equal to charge per unit area. Now we can use this expression to rewrite potential as QD by epsilon naught A. So this is your potential. Now we know, as we have done in the initial lectures, that capacitance was equal to charge per unit potential. Now by using this expression, we can easily write capacitance equals to Q over, instead of V, we will be writing the above expression, that is QD to epsilon naught A. So our capacitance will come out to be epsilon naught A by D. So this is the expression for capacitance of parallel plate capacitor. Next we will be doing some numericals on this topic.